here we have this example. We have a racing car passes a finishing line of a race, moving at a constant velocity of 60 meters per second. After 5 seconds, so this is 5 seconds after it crosses the finish line, it only starts to decelerate at 3 meters per second until coming to a rest, right? They want us to sketch the displacement time graph for the motion after the end of the race. In other words, from the time the car moves past the finishing line to the time it stops. So this is going to be a piecemeal or a multi-stage function, right? And we're going to look at that in a second. So before we do that, let's consider, right, what displacement time graphs look like, right, for either constant velocity or constant acceleration, because those are the only two that we're probably going to deal with for a while. Okay. So, Zara, what is constant velocity?
It doesn't change.
Right, it doesn't change, right? And what is the formula for if we want to find displacement if we have constant velocity?
We can use velocity times time to find displacement.
Okay, so I'm just going to make these two little guys here. We have displacement, not speed, and time. And we have velocity and time. So, Toya, what is, if I told you you had constant velocity, what would it look like on a graph? Constant velocity, the velocity never changes.
Would be a diagonal curve, but like it keeps going straight.
Okay, well, it would just be a horizontal line like this. So for instance, this is what constant velocity looks like. If I told you the velocity is 60 meters per second.
I thought that was constant acceleration.
Okay, no, well, constant velocity. So that's why we want to clear this up before we. So this is, now have a look, I've drawn this on my velocity time graph, okay? I have constant velocity. In other words, I have my gradient for my displacement function is going to be constant, right? Not changing. And Dominic, what kind of graph has a constant gradient? A gradient that never changes?
A straight line graph?
A straight line graph, right? A straight line graph has a constant gradient, right? The gradient doesn't change. If you had to take the derivative of a straight line, you would just get a number, right? So if we are talking about a displacement time graph where we have constant velocity, you can see we're going to get a straight line. Okay? And we would be using here the formula S, displacement equals velocity, velocity times time. And this is just our gradient. So that is a function, right? A function of displacement for constant velocity. So in other words, if I gave you a velocity, so I'm just going to give you a fictitious, well, we can use the one from the example above. If I told you the velocity is 60 meters per second, the function would be S is equal to 60 t. That would be your velocity or your displacement function, okay? If I want the displacement after 1 second, I put t equal to 1 in there, and it will tell me I will be 60 meters away, okay, because I'm traveling at 60 meters per second, right? Because my velocity is the same, If I put t equal to 2, well, it will give me 2 times 60, which is 120. And if you think about it, if I travel 60 meters every second, after 2 seconds, I will be 120 meters. So this is the function for constant velocity. Okay. Right, now let's consider constant acceleration. So let's work this backwards this time. Let's go in the opposite direction. So Keanu, tell me, this is acceleration versus time, right? Tell me, what would constant acceleration look like? What would the graph look like for constant acceleration?
Where the gradient is equal, or it's a straight line.
Right? It won't be a straight line, it will be a. Think about constant velocity. What did the line for constant velocity look like?
Yeah, but I mean, what I mean is that.
Oh, you mean it'll be a horizontal line like this?
Yeah.
Yeah, well, that's exactly what
straight
it is.
line.
Well, this is a
Constant line with the gradient to 0.
horizontal line, okay, with no gradient. Okay, so in other words, it doesn't matter at what time you take this acceleration, you can see it will always be the same, right? It's not changing. For any point in time, you can see on that line, the acceleration remains the same, okay? So Zara, what will this do to my velocity, right? Because acceleration affects velocity. Here's my velocity time. What kind of velocity would I get if I have constant acceleration?
Didn't you also have constant velocity then?
You wouldn't have constant velocity. Remember, the velocity is changing, but it's changing at a constant rate. So let me rephrase this. If I had constant velocity, I have a straight line displacement.
Yeah.
So if I have constant acceleration, I'm going to have linear velocity, okay? Because the gradient of my velocity function is the same everywhere because the acceleration doesn't change. So let's have a think about this. What was the new gradient or the function for my velocity if I have constant acceleration? Well, it's a straight line. So remember, we learned this thing where velocity was equal to, who can remember?
Displacement over time.
U plus a t. Y equal to mx plus c. In other words, here's the gradient, right? My acceleration is my gradient, right? And you can see that the gradient doesn't change, which is by definition what a straight line does, okay? Right, who can venture a guess? If I have a linear velocity, what's my displacement going to look like? Here's my displacement time. What's my displacement going to look like if I have linear velocity? The gradient is changing, okay? But it's changing in a linear direction. So Toya, let me ask it to you like this. If I gave you the gradient function, right? The gradient function came from somewhere, didn't it? And we learned how to find that function. We called it the primitive. If I had to anti-differentiate a straight line, what graph would I get? So when we anti-differentiate, we find the primitive, so we raise the power of everything by 1, don't we?
Yeah,
Would
and
be an
then
X
divide
squared,
it by the new power.
Yeah.
So wouldn't that be the curve?
Exactly. So if I take a straight line, the highest x is x to the power of 1. If I anti-differentiate, I'm going to get x squared. In other words, I'm going to get a quadratic. Okay. So if you have linear velocity, right, you're going to get a quadratic displacement. Right? In other words, when I'm trying to, if I'm trying to find an equation or sketch it, I'm going to be looking for my displacement as a function of time, right? But it will have some kind of equation like that. Okay? The same for deceleration. Okay, deceleration would work. So if the velocity was negative, the curve would just be an unhappy parabola. Okay? So I thought we'd look at this, right? Now we have an idea of what the graphs are going to look like when we have to draw them. Okay, if we have constant velocity, you can see we're going to get a straight line. Right? If we have acceleration, constant acceleration, we're going to have a curved line like this.